This video is the first of two parts in which we will go through several time value of money example problems to illustrate the important time value of money concepts. Now, I just went to Google, typed in time value of money sample problems, and this was one of the first things that popped up. I figured many people have put time value of money sample problems up online, and so looks like we have 27 problems here. And so we're going to work through each one of these, try to get through at least half of them in this video and then half in the next video. I assume that you've already looked at the lecture notes, and here they are. They're on my website. I assume you've already looked through the lecture notes for the time value of money concepts. Basically, in the lecture notes, we derive 6 formulas, and from these 6 formulas, you can solve any time value of money problem. I will say almost any. When it comes to solving for the interest rate, R in this case, you do need another technique. And I'm talking about solving problems without using a financial calculator. You still need to use your calculator to calculate, to plug into the formulas that we have, but without using the financial application on your calculator. That's what I'm talking about, and that's what we're going to try to do for every one of these problems. Sorry about this pop-up box. It always pops up. But for the interest rate, solving for the interest rate, it turns out you need another tool known as Newton's method. But I'm not going to give that to you in this video. We'll talk about it at the end of the course. So any problem where you're trying to solve for the interest rate, we'll just skip over, and I'll refer you to Newton's method. If you know Newton's method, you can solve for the interest rate. But for every other problem, all you need are one of the 6 formulas or several of the 6 formulas in these lecture notes. So we have the future value of a single amount and the present value of a single amount. The future value of an annuity due, the present value of an annuity due. An annuity is just a steady stream of equal fixed payments. And the annuity due means that the payments occur at the beginning of a period. And then we have the future value and the present value of an ordinary annuity. And that's where the payments occur at the end of the period. Hence the word ordinary. Ordinarily, people get paid at the end of a period, and therefore they make payments to the bank, for example, at the end of the month. Or I guess that's the reason why they call it an ordinary annuity. So we have these 6 formulas in the lecture notes. Equations 1, 2, 3, 4. I think I have them labeled as such. Yeah, 1 through 6. And then I had some examples in the lecture notes of how you might use these formulas. For example, we looked at how to calculate the monthly payment you would make to the bank if you take out a loan for your house. Or, for example, suppose you want to send your child to college in 18 years. How much do you need to put in the bank now to be able to afford college in 18 years? Or if you can put money in the bank every year, how much do you put in? So that's an annuity one. So I did a few examples, but in this video we're going to go through several more examples, starting right here, to try to illustrate these concepts. Now these examples will start off in level of difficulty rather easy, and they'll move to a little bit more difficult. So number 1, excuse me, you wish to accumulate $140,000 in 13 years. How much do you need to put in the bank today, or in the account today, if it pays an annual interest rate of 14%? All right. So we want $140,000. And we know from lecture notes, if we put an amount P in today into an account that pays 14%, then at the end of 13 years, the account will have this much in it, right here. But we know what that is. It told us it would be $140,000. So it's giving us the future value of this account, and it's asking us for the present value. In other words, what amount do we need to put in today, P, such that if we leave it in that account for 13 years and it generates interest 14% every year, interest compounds once per year annually, then we'll have $140,000. So we just solve for P. And you'll find that P is approximately equal to 25,000. I've already solved these. Let me look here. 489.71. And let's just suppress the decimals here. Just round to the nearest dollar. Remember from lecture, the future value of an amount P invested today, invested once, a single amount, at an interest rate of R, and let sit for n compounding periods, is this. R is the interest rate per compounding period, always. N is the number of compounding periods. The interest rate they give you in any problem that you'll always be given is stated as an annual rate. But if interest compounds other than annually, if it compounds monthly or quarterly, then the rate they give you, you have to convert it to the rate per compounding period. And if it doesn't compound annually, it compounds monthly, then the annual rate they give you, that's not the rate, that's not R, that's not the interest rate per compounding period. R in the formula is the interest rate per compounding period. You'd have to convert it to a monthly rate or a weekly rate or a quarterly rate or whatever, how often interest compounds. And all we mean by interest compounds, we just mean interest is paid. Interest is either paid monthly, weekly, quarterly. Because if you get interest, then you can start accumulating interest on that interest as soon as you get it. So if you get it weekly, you can start accumulating interest on the interest that you just got weekly. And that's why this R here is a interest rate per compounding period. And then N is not necessarily the number of years. If interest compounds annually, then N is the number of years. But if interest compounds anything other than annually, N is always the number of compounding periods, right? So if interest compounds monthly, N would be the number of months. Weekly, N would be the number of weeks, and so forth. So that's just a little review from lecture notes. All right, let's go to number 2. What will $247,000 grow to be in 9 years if it is invested today in an account with an annual interest rate of 11%? That's just asking us for the future value of the $247,000. Put it in an account today. It's getting 11% interest. We leave it there for 9 years. It's 11% interest is compounding annually. So this is the annual rate. This is the number of years. And we will see that the account will be worth, if we round to the nearest dollar, I'll have to do it in my calculator because I don't have it. Let's see here. 1 times 247. So it would be 631,835 at the end of 9 years. I should change this to a approximate because it's not exact. The formula is exact, but this answer is not exactly right because we rounded. Number 3. How many years will it take for $136,000 to grow to be $468,000 if it is invested in an account with an annual rate of 8%? So we invest $136,000 at 8% per year. Interest compounds once per year annually. We let it sit there for n years, and we know it'll be worth $468,000. And the question is, what's n? How long does it take? So we need to isolate n. Let's first isolate 1.08 to the power of n. Divide both sides by 136,000. 468,000 over 136,000 is the same thing as 468 over 136 because the 3 zeros cancel each other. Now we need to isolate n. In here we use the natural logarithm, or the logarithm. It doesn't matter which logarithm you use. Logarithms have the property that the log, whatever the base is, it doesn't matter, of some number to the power, to any power, is equal to that power times the log of that number. This is a property for any logarithm. In other words, for any b. Logarithms could have any base, right? I want to use a natural logarithm. It'll come in handy later. The natural logarithm we abbreviate as ln is, so the natural logarithm of a number, well, let's keep our notation. the same. The natural logarithm of a number, say m, is just the logarithm base e of that number. It's just another way to write this. ln takes the place of log base e. So we're just different notation. So we're going to use a natural logarithm here. And this will come in handy later. So if the left-hand side equals the right-hand side right here, then the natural logarithm of the left-hand side equals the natural logarithm of the right-hand side. And now we invoke this property right here. The natural logarithm of a number raised to any power is just that power times the natural logarithm of that number. And the right-hand side doesn't change. And then n equals the natural logarithm of the right-hand side divided by the natural logarithm of 1.08. And if you do that in your calculator, you will find n is approximately 16 years. It turns out it doesn't matter which logarithm you use here. You can use log base 2, log base 10, log base 3, log base 5. On your calculator, there are two log buttons. There's a log and there's an ln button. This button means log base 10, and this obviously means log base e. It doesn't matter which log you use, you're still going to get 16 years as the answer. But the reason we're using this particular one right here is because I want to be consistent. Later on, we're going to need to use that particular one. You'll see it here just coming up soon. Whereas the other ones won't work for the problem we're going to do here in a second. Actually, it's this problem right here, number 4. Number 4 asks, at what annual interest rate must $137,000 be invested so that it will grow to be at $475,000 in 14 years? So it's asking for an interest rate here. We know the $137,000. If we let it sit for 14 years at an interest rate R, it will grow to be $475,000. This is the equation that describes that, right? And the question is, what interest rate do we need to be getting on this investment per year for this equation to hold? That's the question. So we need to isolate R. In general, solving for the interest rate is tricky. This is a particular case where it's not. We can actually solve for it. Or you might feel that it's tricky still, but you can actually solve for it using some, there's a closed form expression for R from this equation. But if this was an annuity and we're trying to solve for R, there isn't a closed form expression in general for R. You have to approximate it using some root finding algorithm such as Newton's method. But we'll talk about that later when it comes up. So let's isolate R. First, let's isolate 1 plus r to the power of 14. That's the first step at isolating R. So divide both sides by 137,000. Now how do we get R by itself? Now we're going to use this property up here of logarithms. And we're going to use the natural logarithm here. Take the natural logarithm of both sides. And we know the natural logarithm of any number. 1 plus r is any number, right? That qualifies as a number. Any number to the power of anything is just that power times the natural logarithm of that number. And then we can solve for the natural logarithm of 1 plus r. It's just 1 over 14 times the natural logarithm of the right-hand side. Now we need to isolate 1 plus r so that we can isolate r. This is why we use the natural logarithm. Well, it turns out you could have used any logarithm here again. But if you use the natural logarithm, what undoes the natural logarithm? How can we get rid of this natural logarithm on the left-hand side? Well, we know that log base e is the natural logarithm, right? So that means that e, the number e, which is familiar 2.71 blah, 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 constant that you've seen from mathematics. We know e and the natural logarithm are inverse functions of each other. So e to the x and the natural logarithm of x are inverse functions, where x is anything, right? X can represent anything, including 1 plus r. X is any number. All this means is that e to the natural logarithm of x is equal to x. And also the natural logarithm of e to the x is equal to x. So they undo each other. If you take the natural logarithm of x and then take e, raise it to that power, you're left back with x. If you take e and raise it to the power of x and then take the result, take the natural logarithm of the result, you're back to x again. They're inverses of each other. So this should be familiar from grade school mathematics, I think. I think you would have learned that in grade school. So that means we can take e and raise it to the power of both sides. If you do it to the left, you got to do it to the right. These cancel, so we just have 1 plus r on the left. On the right hand side, you can't cancel the e with the natural logarithm because there's this 1 over 14 outside. If we put the 1 over 14 back on the inside, then you could cancel, but we'll just leave it like it is. And then we're one step removed from finding r. All we have to do is subtract 1 from both sides. And we found the interest rate that you need to be able to get in order for that original equation to work out. So all you have to do is put this into your calculator and you're golden. And if you do that, you're going to find that r is approximately 0.0929 or 9.29%. Moving on, number 5. If you wish to accumulate $197,000 in 5 years, how much must you deposit today in an account that pays a quarter annual interest rate of 13% with semi-annual compounding of interest? So we know if you put in P today, if interest is compounding at 13%, but remember R in the formula is the interest rate per compounding period. So per compounding period, if interest compounds twice per year, the interest rate every 6 months would be 6.5%, or 0.13 divided by 2 to the power of n, which they said 5 years, but interest compounds twice for each of those 5 years. So that's 10 semi-annual periods. And they said it would be 197,000. We're just trying to figure out what we need to put in there today. Is that right? Yeah, right here. No, sorry. We're part 5 here. There. So we just have to solve for P. And you can quickly see that you just divide both left and right hand side of the equation by 1.065 to the power of 10. And you will find that P is approximately $104,947. If you put in that amount now, then after 5 years, it will have grown to 197,000, assuming interest compounds at 6.5% per half year. And we have 10 half-year compounding periods in 5 years. Number 6, what will 153,000 grow to be in 13 years if it is invested today in an account with a quoted annual interest rate of 10% with a monthly compounding of interest? Well, we're just using the same formula over and over and over. here we have monthly interest rate, and how many years did it say? 13 years? 13 years, yep. Well, in 13 years, there's this many months. Remember, n is the number of compounding periods, and interest compounds monthly in this example. So n has to be 13 years times 12 months, how many ever months that is, right? 130 plus 20, 156, I believe. So you just do this in your calculator, and you will find that it's approximately, it will grow to be 558, 386. Obviously, you can see, I think, from the formulas that the more often interest compounds, the bigger you're going, the more you're going to have in the account at the end of the investment period. Holding everything else constant. Also, holding everything else constant, the more, the bigger the initial amount you put in, the bigger your output's going to be. That makes sense. So let's move on. I guess the question is, which one affects the final output more? What you put in at the beginning, or how often interest compounds, or how many years you let it sit there? It turns out you can do some sensitivity analysis, and you will find that what affects this the most is this. How do we determine that? For a 1% increase in this goes up more than a 1% increase in this, or in how often interest compounds. So turns out that this is why you always hear in the popular press, and even from financial advisors, that's where the popular press got it from, I assume, that if you just start saving early, whenever you're young, whenever you're in your 20s, if you start saving for your retirement, there's a much higher likelihood you're going to have 1, 2, 3 million in your account, more money in your account at the end than if you start saving whenever you're 35, for example, when you're making a lot of money. That just speaks at this notion that doesn't matter, because when you start saving early, this isn't very big, right? You're not putting very much in at the beginning. But if you start saving early and you do it all the time until you retire, this becomes reasonably large, and that's what's going to affect this the most. So this is why you get this advice. Now let's move on. Number 7. I could do the partial derivatives for you, the sensitivity analysis for you, to show you why the number of years is the most influential of the final output versus what you initially put in or how often interest compounds. I could show you that, but I won't. It just takes up extra time. Just take my word for it. How many years will it take for 197,000 to grow to be 554,000 if it is invested in an account with a quoted annual interest rate of 8% with monthly compounding of interest? So they're asking for n again. They're asking for the number of periods. 197,000 we invested at, I've already forgotten, 8% annually, but interest compounds monthly. And we know it's going to grow to 554. And the question is, how many, in this case, months then? N is months. How many months will it take? Well, we can just solve this equation for n, just like we did before. First, isolate this by dividing both sides by 197,000. Then take the natural logarithm of both sides. And then invoke the property of natural logarithms. Natural logarithm of any number raised to any power is that power times the natural logarithm of that number. And then we solve for n. And you'll find that n is approximately 156 months. So that's the answer, but then it asks, I think it doesn't ask for months, so it asks for how many years. So careful with that. So you can just figure out how many years by just dividing by 12. 12 months in a year. And you will get basically 13 years. So, there you go. Moving on to number 8. Let's see how long this video is. 25 minutes? Alright. We don't want to make it more than an hour because it takes too long to upload to YouTube. Number 8. At what quoted annual interest rate must $134,000 be invested so that it will grow to be $459,000 in 15 years if interest is compounded weekly? So they're asking for the interest rate. Whenever they ask for an interest rate, just be careful because you can't always solve for it. We know that whatever this rate is, it's a weekly rate. And how many weeks? 15 years. So 15 years, and there's 52 weeks in a year, so n is that, 15 times 52. And what is it going to grow to? 459,000. So we set up this equation and we solve for r. We solve for r using the same thing we did earlier. First of all, what's 15 times 52? 75. Oh, no, not 75. 780 weeks. And we will have this. Divide both sides by 134,000. Then take the natural logarithm of both sides. Don't forget to take the natural logarithm of both sides. Whatever you do to the left-hand side, you have to do to the right-hand side, because we're saying they're equal. If the left and right-hand sides are equal, then we have to do the same thing to both sides. This is an equation, an equality, not an inequality. So here, to isolate 1 plus r, now we invoke the property of logarithms. We take out the exponent. And then we divide both sides by 780. And then we need to isolate r, or we need to isolate 1 plus r first. So we do that by we have to get rid of the natural logarithm. So we take e and raise it to the power of both sides. And that gets rid of this over here. So we have, basically then we have r equals the right-hand side minus 1. I did 2 steps to go from here to here. And if you put that in your calculator, you're going to get that r is approximately 0.16%. You would actually get 0.0016, but in percentage terms, you multiply that by 100, it's 0.16%, right? But that's a weekly interest rate, right? Remember, r always in the formula. R is always the interest rate per compounding period, per week in this example. But they don't ask us for the weekly interest rate. I think they ask us for the annual interest rate. Yeah, at what quoted annual interest rate? So we just take this, multiply it by 52 weeks in a year, and we'll get the annual interest rate. Approximately 8.21. Number 9. You are offered an investment with a quoted annual interest rate of 13% with quarterly compounding of interest. What is your effective annual interest rate? This is you haven't seen this in the lecture notes yet. But what this means is, let's do an example. Suppose you take $1,000 and you invest it at 10% for 1 year. What do you have at the end of the year? How much money do you have in the account? You have $1,100. Right? What is your return? Or what is your rate of return? What is your interest rate? 10%, right? It's the amount you have at the end minus your initial investment over your initial investment. 100 over 1,000, 10%, or 0.1. What if instead you take this 1,000, you invest it, it's 10% per year, but the only thing we add to it is interest compounds monthly. Then what do you have at the end of a year? Well, you have your 1,000 times 1 plus 0.1 divided by 12 raised to the power of 12. 12 compounding periods. Just using the formula. Up here we just used 1,000 times 1 plus 0.1 raised to the power of 1. And you got 1,100, right? But down here, interest compounds monthly, so the monthly rate, number of months, and you'll find that you have $1,104 and some change. Well, let's see exactly how much do you have. 0.1 divided by 12 plus 1 raised to the power of 12 times 1,000. Yeah. You have that much. So you have an extra $4.71. The money stayed in the account 1 year, just like it did in the first case. But interest compounded more often. You were paid interest more often. So it was more often the case you were able to generate interest on interest. And that basically amounted to $4.71. What's your rate of return in the second case? Your rate of return in the first case is 10%. What's your rate of return in the second case? Well, here's what you have at the end, minus your initial investment, over your initial investment, 10.47%. This is known as the effective annual rate of return. The effective annual rate of return, in words, is just the rate of return that makes you indifferent between investing at that rate where interest compounds annually or investing at the quoted rate where interest compounds something other than annually. In this case, you're indifferent between taking $1,000 and investing it at 10.47% where interest compounds once per year and you invested for 1 year. You're indifferent between that or taking the $1,000 and investing it at a 10% annual rate but interest compounds monthly. Why are you indifferent? Because under either scenario, you would have this much at the end of the year. That's the effective annual interest rate, or the effective annual rate of return. When interest compounds annually, the quoted interest rate and the effective interest rate are always the same. But when interest compounds something more often than annually, then the effective annual rate of return is always going to be bigger than the quoted annual rate of return. When interest compounds less frequently than annually, so maybe interest compounds once every 2 years, then it will always be the case that the effective annual rate of return is less than the quoted annual rate of return. When interest compounds annually, then we already said that the two are equal. Or more often in this case, right? Interest usually compounds, either if it doesn't compound annually, it compounds more often than annually. I mean, who's going to wait 2 years for interest to compound? 2 years to get interest. So usually in this case, the case where the effective annual rate is greater than the quoted annual rate. Why is the effective annual rate of return, how could it be useful? Well, it's useful in comparing investments where the two investments differ based on how often interest compounds, right? So if you have one investment where interest compounds weekly, and say it has a quoted rate of return of 10%, and you have another investment where interest compounds monthly, and it also has a quoted annual rate of return of 10%, which investment's better? Say you're going to invest in both investments for the same amount of time. Well, you can't compare. It's hard to compare. It's like comparing apples to oranges. But if you calculate the effective annual rate of return for the weekly investment versus the monthly investment, then you will be able to compare the two investments. Whichever one has the highest effective annual rate of return will be the better investment, because that's the one that is going to give you the most money at the end of the period. So we didn't go over that in lecture, but we just did then. It's a little mini lecture here. Took up a little more time than I wanted it to. So let's go ahead and look at the question one more time. You have an investment, quoted annual rate of 13% with quarterly compounding. What's your effective annual interest rate? To calculate the effective annual interest rate, it's equal to 1 plus the quoted annual interest rate divided by, let's just call, what do I want to, I'll just put number here, where number is the number of compounding periods per year. So to find the effective annual interest rate, you just take 1 plus the quoted annual interest rate divided by the number of compounding periods per year, raised to the power of number. That's an equation for the EAR. So in this case, the EAR is 1 plus the 13% quoted annual rate. It said interest compounds weekly in this, quarterly in this example. It's quarterly compounding. So there are 4 quarters in a year, raised to the power of 4. And then subtract 1. There's the formula. And so you will find that 0.13 divided by 4 plus 1, raise all that to the power of 4 minus 1, approximately 13.65%. You get 0.1365 approximately. That's the effective annual rate of return. It's quoted at a 13% rate, but since interest compounds quarterly, your effective rate is going to be higher than that. In this case, 13.65. What's the rationale for this formula? Well, basically the rationale is if you take $1 and you invest it at 13% and interest compounds quarterly, then after 1 year, how much money are you going to have? You're going to have $1, 13.65 cents, right? So what's your rate of return? It's that minus 1 divided by 1. So really we need to divide by 1 here, but any number divided by 1 is just itself, so there's no need to divide by 1. And this dollar, it could be $1, $10,000, $25,000. Without loss of generality, we can just consider $1. $10,000 is just 10,000 $1 bills. All right, 10. You are offered an annuity that will pay. You are offered an annuity that will pay $24,000 per year for 11 years. The first payment will occur 1 year from today. So the annuity happens at the end of every period. You feel that the appropriate discount rate is 13%. What is the annuity worth to you today? I hate when they say discount rate, but basically what they mean here is you feel that every time you get $24,000, you can take it immediately That's the assumption here. Because if you can't do this, then everything breaks down. There is no time value to money. But you can take the $24,000 immediately and invest it in an interest-bearing account, where interest on that account accumulates at 13% per year. That's what they mean by the appropriate discount rate. So here we have an annuity, and they're asking for the present value of that annuity. Now we've gone through this in lecture notes. I'm not going to go straight to the formula though. I'm going to reason again like we did in lecture notes, like we did in the lecture. You could take the 24,000 and you could invest it every time you get it. And you get it at the end of every period. At the end of every period, you put it into an interest-bearing account that bears interest 13% per year. And you let it sit there, how often do you do this? 11 years. Then at the end of the 11 years, how much will that account have in it? Well, it will have this much in it. This is the future value of an ordinary annuity. Formula straight from lecture notes. Here, I'll show it to you. Right here. So you'll have that much in at the end. The question is, what's it worth to you today? Well, you're indifferent between doing this or taking an amount P right now, once, investing it, getting 13% per year, and at the end of 11 years you will have this much. So if you're going to be indifferent between this and this, that means that they should be equal to each other. No matter which investment you do, whether you do the $24,000 every year, at the end of every year you put that in and you get 13%, or you just get an amount P now, put it in once, and you get 13% every year. You're indifferent between these two. And then solve for P. And that's what the annuity would be worth to you today. That's what this would be worth to you right now, whatever P is. It's the present value of an ordinary annuity. So P equals 24,000 times 1 plus 0.13 to the power of 11 minus 1 over 0.13. So all of that over 1.13 to the power of 11. Right? We could do this. That's going to give us the answer. Or we can just use the present value of an ordinary annuity formula from lecture notes, which would be the formula number 6 right here. We could just use this formula and we would also get the same answer. But notice how we got this formula. We got it from this line right here. And what's this line right here? This is what we just wrote right here. And then you solve for P. In this case you solve for PV. But PV right here is the same as P down in what we're doing right now. What did you just took this right here and you divide by this. And then we did some algebra to rewrite it. You end up just getting this. Right? So it's the same thing. This right here is exactly the same thing that you would get as if you did this. Right? So solving, you would get 136,487 if you round to the nearest dollar. This $24,000 annuity at 13% per year, invested for 11 years, right now is worth to you $136,487. Moving on to number 11. Let's see how much time we have left. 15 minutes. Number 11. If you deposit $16,000 per year, If you deposit $16,000 per year for 12 years, you make each deposit at the end of each year into an account that pays annual interest of 14%. What will your account be worth at the end of 12 years? That's just the future value. They're asking for the future value of an ordinary annuity. And we already know the formula. It's the amount that you put in times 1 plus the interest rate, the periodic interest rate, raised to the power of number of periods, minus 1 over that periodic interest rate, which I can't remember what it said. Let's see, 14% interest compounds annually, so it's 14%, and we have 12 years. Oops. So at the end of 12 years, you would have this amount, which approximately is equal to 436,331.98. Well, let's do to the nearest dollar, it's just this. Number 12. You plan to borrow $389,000 now and repay it to the bank in equal annual installments, 25 equal annual installments. And you'll make payments at the end of each year. If the annual interest rate is 14%, how much will your annual payment be? Well, to answer this one, we can reason from the bank's perspective. From the bank's perspective, they're indifferent between. One thing they could do is they have two alternatives. They could take the $389,000, don't lend it to you, but put it in an interest-bearing account, an account that bears interest at 14% per year, and leave it in there for 25 years. At the end of 25 years, this is how much they would have in their account. That'd be the future value. They're indifferent between doing that or another alternative, which is lend you the $389,000. Now, you give them P dollars per year. At the end of every year, you pay them P dollars. They take that P dollars and immediately put it in that same interest-bearing account that's getting 14% per year. If the bank does that for 25 years, every time you pay them that P dollars, they take that P and immediately put it into that interest-bearing account and get 14% interest, and they do that for 25 years. What will that account be worth to the bank at the end of 25 years? Well, that would be the future value of an ordinary annuity, right? So the account would be worth this. So the bank has alternative 1, alternative 2. They're indifferent between these two if they're equal. If they could have the same amount in each account, then they're indifferent between lending the money to you and getting P dollars every year, or not lending the money to you and just putting it into an interest-bearing account. They're indifferent between these two if the ending values are equal, and we can solve for P, which would be the amount that you pay the bank per year. So you would pay the bank this divided by this. Hopefully that makes perfect logical sense. This is exactly the same way to figure out the monthly payment you make on your house for a mortgage. So you will find approximately you will pay the bank per year $56,599. Yay, messed up there. $56,599 a year. All right, number 13. You are told that if you invest $11,000 per year for 23 years, all payments made at the end of each year, you will have accumulated $366,000 at the end of the period. What annual rate of return is the investment offering? Here they're asking for you to find the interest rate. And this is an example of where you can't find it. There's not a closed form solution for it. You have to approximate it. So let's set up the problem. You invest $11,000 a year for 23 years. You're going to get some interest rate per year, R. Interest compounds once every year, so we don't have to convert R to a monthly rate or anything like that. And we're told that it would grow to $366,000. The future value of that annuity would be $366,000. And the question is, what rate you need to be able to get on that account for that to happen, for this equation to hold. Well, to figure that out, you have to solve this equation for R. So let's start to solve it. Let's start to solve it for R, and you will quickly see the problem. First, divide both sides by 11,000. And you already see the problem, I think. Now we can multiply both sides by R. But we see R is in two places, right? If we rearrange, we would have this. And right here, you see we have a polynomial of degree 23. And we're trying to find the places where that polynomial crosses the R axis. Or in other words, we're trying to find the roots. If we let this polynomial be called f of R, it's a function of R. So we graph R, or f of R versus R. And the polynomial looks something like this, right? And we're trying to find all the places that the polynomial crosses the R axis. In other words, where the function, here's the function, f of R, equals 0. Where does that happen? It equals 0 at these places. The function, I mean, if we go up here, this might be 100, but this is 0, right? The function equals 0 at these places. You can see there could be multiple values of R which make the function 0. But they're asking us for one interest rate, right? So you quickly see that it's there's a problem here. And in general, when you have a polynomial of degree n, where n is any number, the polynomial has at least n roots, but it doesn't. You're not sure how many of those roots are real roots versus how many of those roots are complex number roots. So I don't want to get too much into higher level math, but there is in general no closed form solution for R for polynomials like this. But one method that you can use to approximate R, you have to approximate it. One method that's famously known, Isaac Newton devised the method, Newton's method, and it's a method that your calculator, whenever it tries to approximate roots, it uses some form of Newton's method. It's programmed into the calculator. But you have to use some approximation to figure out the values of R that make the equation 0, or the roots. And you can toss away all the negative ones because we don't care about negative interest rates. Those don't make sense in this context. You can toss away all the complex R's because we don't care about that. Just the positive real R's. If there's more than one, we can toss away the ones that are, well, I don't like tossing away any ones because they're roots of the equation, right? Hopefully there's only one real R, positive real R that makes the equation 0, and that would be the interest rate. Now it turns out if you did Newton's method for this one, you would find approximately R equals 3.21%, or 0.0321. So that's the answer to this one. I don't have time to go into Newton's method though to show you how to derive that answer. Obviously, if you have a financial calculator, there's an app on your calculator that can calculate the root for you. But I'm telling you, what that app is using Newton's method programmed into it. So I think that we've almost run out of time for this video. Let's see how much time, 53 minutes. We might have time for one more. Let's do number 14. You are offered an annuity that will pay $17,000 per year for 7 years. The first payment will be made today. So the payments are made at the beginning of every period, beginning of every year. You feel that the appropriate discount rate is 11%. What is the annuity worth to you right now? Well, we've done this already. We could take the 17,000. If we put it in today, and we're getting 11%, and we do this for how many years? 7 years? Yeah, 7 years. Then at the end of 7 years, what will the account be worth? Well, that would be the future value of an annuity due formula. Future value of an annuity due formula is just like the future value of an ordinary annuity, except we have to multiply by an additional 1 plus R right here. You can verify that in the lecture notes. Go verify it real quick. See, when we're looking at the future value of an ordinary annuity, we don't have to worry about right here, right? We don't have to worry about that extra 1 plus R, but future value of an annuity due right here. There's this additional 1 plus R, because at the beginning of that first period, we immediately put money in, so we get that additional interest on it. That's sort of the logic, the intuition behind it. And we derive these formulas mathematically. I'm not going to go into that again. So if we did the 17,000 at the beginning of every period for 7 years, and we're getting 11% per year, then that annuity would be worth that at the end of the 7 years. What is the annuity worth to us today? Well, we're indifferent between doing that or just taking amount P right now and investing it once getting 11% each year for the next 7 years. And at the end of 7 years, we would have that in the account. We're indifferent if the two amounts are equal, right? So the annuity to us today would be worth P. Just solve for P. In other words, find the present value of an annuity due. And you can just use the present value and annuity due formula from lecture notes, or you can do the logical reasoning that I just did there. That's exactly what we did to derive the formula in the lecture notes anyway. But yeah, you can use this formula right here. Notice this 1 minus this to the negative n. Or you can just do the reasoning that we did from this step. You divide to find this, which is what we're trying to find in this problem. You just take this and divide it by this, which is all we did. And you can rearrange algebraically and it turns into this formula, but the same thing algebraically. So you end up getting today that this annuity is worth to you $88,919. Alright, this concludes part 1 of the video on time value of money.